What's up, guys? Doing a little early stream today. Hopefully get some research in, do a little Bloons TD6. Never played the game before, but people are all about it, so I thought maybe I'll give it a shot. What's up? We got Jeez Louise, Nate the Great, Nathan Ochi. What up, guys? Hope everyone's having a good Saturday. What's up, Akash? Anyone played this game yet? Bloons TD6. Look at it's getting rave reviews. If you look at the store page, overwhelming 97%, 96%, overwhelmingly positive. I didn't realize it was released that long ago either. It's like almost 2.5 years ago. What's the name of the song? Good question. Let me see if I can figure it out. I forgot what it is. I think it was supposed to be copyright free because I wanted something I could play at the beginning that was copyright free, and I think it was, but apparently maybe not. I'm actually kind of worried now because I got a notification of something about it, so it might not be copyright free. But let me see what it is. Let's see what I find. Let's see, this was all right. It's the very first song. On this it's the opening song on this video. So if you look at the video, the title says no copyright, right? So that's why I assumed I could use it. I'm looking at the top comment on it. It says, all songs are safe to be used. Nobody will strike your video, even if you don't credit the artist. In case your channel is approved, you want to monetize using the song, just send an email. Okay, Yeah, looks fine. right, that's a little loud. Huh? Bloons have taken over your town. Stop the Bloons from getting through. It's basically just a classic tower defense game. Settings here. Kingdom Defense. Or Kingdom Rush. Okay, cool. I don't... I want the music on. All right. Okay, upgrade. Each monkey has 5 upgrades. In 3 paths, unlock one of them now. Long range, quick shots, sharp shots. Oh, it looks like it's forcing me to do sharp shots right now. 1 extra one per shot. You've unlocked the upgrade, but still need to apply it to the monkey's tap.
Are you kidding me? Nothing gets past my bow. You want some?
What does this one do? Proud, strong, I could use this, but choose a monkey to unlock. Ice monkey pops and freezes nearby balloons for a short time. Frozen balloons are immune to sharp damage. Can't freeze. Why does it burn? Shoots a blob of sticky glue. Launches a powerful bomb. Slow rate of fire, but affects a radius around the explosion. That's actually pretty good. Shoots a short range volley. Sharp attacks. Rolls a boomerang that follows a curved path. Good range and pierce. I want this one. It's a pretty small range, actually. Probably go right there. So you want to place these things right where they have the most path covered. That seems pretty good right here. Actually, maybe like right there. If anything even gets through there.
Yes.
What
Yeah?
Level 2. So far, so easy. Shoots larger bombs. Reloads faster. Extra range. Wait, didn't I just do that? Oh, you... Okay, got it. Oh, I see it go... Wait a minute. So if I upgrade the quick shot, you unlock it. Oh, and then you have to buy it? What's up, Geez Louise? Thanks for the hydrate. Today I just got some coffee here. So you unlock it with experience. Then you have to actually purchase it. Okay.
All right.
You have an activated ability. These create powerful temporary effects to help you win. Choose carefully when to use them. However, as each one has a cooldown.
Yes?
Oh, down here? Let's see. Pops and freezes nearby balloons. I like this one. One round to go. Should save my money. This has been too easy. I'm not worried. I am not worried about any balloons getting by. This guy's just not saving any balloons for anybody else. Uh-oh. Oh, it's easy. That was the tutorial. Yeah, I don't know what the premise is of the game. Resolution. Thanks for the follow, Avocado Momo. So, this doesn't have an option. Wait, let's not do full screen. I don't like to have my games in full. I don't know if anyone else has the same feeling, but like when I have a game in full screen, it feels too it takes up my whole thing. Like I feel so locked into it. I like to have it in a windowed mode. Wait, if I do non-full screen, no, that's not right. We need to do, no, not that one. 1600 by 900. That's not bad. This is gonna be too tall. Yeah, let's do 16 by 9. Win games to earn medals. Okay. Yeah, I wonder what this is, by the way, this is the 6th game in this franchise, apparently. Monkey money. Okay. This better not be one of those pay to win games, because it was not, but it shouldn't be, because it wasn't free. Okay, these are just like achievements. I wish, you know what, more games need to have that is an underrated setting with screen size is just, I should just be able to adjust the window to whatever size and scale I want. Like I shouldn't have to select from your pre-described menu here. I wish I could just grab the edge and just drag it to make it whatever I want. Like that's just the, got to program that in. It's just too good of a feature. What's up, mechanisms, forces? PVZ will always be the best strategy game. PVZ was really good. That's an old game though now. Monkey Meadow. Wait, do I just pick? Is there no progression here? I can literally pick any. Let's just start with something simple. Oh, I see. Let's try medium just to see. Apocalypse? Never heard of Apocalypse. Is Apocalypse, these are just tower defense games? All right, this is my, I'm gonna place right there. Seems to be pretty good.
Are you kidding me? Nothing gets past my bow.
I have to get a sense for just how hard this game is. Okay, so I got to make sure, like, so, wait, when I upgrade stuff, am I upgrading that just for this particular game, or is it upgraded across, like, the entire game? Like, so whatever other map I play. Like, so let me see. Actually,
you want some?
It's still, this one's still level 1. Put a dart monkey here. Yeah, see, they're not upgraded. So you upgrade it within the game, it looks like. So every time you start a new map, you start from scratch, it looks like. Can pop 1 extra balloon per shot, shoots 15% faster, makes the dart monkey shoot further than normal. I will do 15% faster. Quick shots. Oh, but see, I already unlocked these. I see. Okay, now I get it. So your experience is what you gain to unlock, and then once it's unlocked, you pay for it whenever you play using this. And this is, I'm assuming you gain this as you win each round. So let's just do this real quick. What's up, Ashi? Do some research today for CRISPR. Is that you feeling like doing that today? Uh-oh. What's up, Joe? I got my cup of Joe here. Let's try this bad boy out. Oh, very narrow range. I'm going to go right there, I think. Actually, ideally, I actually don't know. So if it's, will it shoot anything on the path, even if some of its radius of effect is touching the path? Like, that's what I don't know. No? So if I place this right here, is it possible for like this to hit no balloons? Because the balloons are going to be going like along the path, but not in the shaded area. Okay. Well, then I guess it makes more sense to put it there. Have you played this game, Joe? Oh, mainly 5. I've never played any of them. I played Plants vs. Zombies before. I played some like phone ones. But this is the first time playing this series. So it's 60 rounds. Glue Gunner. Shoots a blob of sticky glue to slow down balloons by 50%. Hurls a boomerang. I like this. The slow down might be good. What are do the different color balloons represent anything? Oh, it looks like clearly the blue ones move faster.
Sweet.
Keep playing. So it looks like blue moves faster than red, and green is like really fast. Oh, more layers. Okay. Got it. That makes sense. By the way, Joe, I heard I just perused over the conversation you were having with Creepy in the Discord about our witch farm, and he was very critical of it. Clearly not a fan. Yeah, he was definitely ragging on Shulkercraft. I had always heard that Shulkercraft was pretty decent, but I feel like Creepy has very strong opinions on certain things. He's got clear preferences. Very particular, which can be a good thing. Apparently steals tutorials from other channels. Oh, that's not so good.
Sweet.
Yeah, he is. It's a good thing, I think. It depends on like the environment you're in, right? Super Monkey Sun Temple is so complicated. Yeah, I saw the one that he posted. What was? Let me see. Did you take a look at it? I didn't look at it yet. This one right here. I'm just gonna take a quick look.
Hi guys, welcome back to another tutorial video. So today I want to show you how you can make the witch farm that I built in my Skyblock world. It's actually an updated version because the way mob spawning works changed again in 1.
Okay, you know it's going to be highly efficient when it's the guy who's talking has a German accent. Got that German engineering mindset.
1.14.3, so we're back to using SoulSend now. So what changed exactly? Mobs don't spawn on top of trapdoors
I have been
anymore, so
playing Minecraft for 14 years. I used to be an engineer at BMW, and I have applied what I have learned to Minecraft, and this is the most efficient farm you could have ever imagined. It will take you 5 years to build, but it will generate more gunpowder than you know to do it. Literal god.
but also spawn proof again. Yeah, it's been actually quite a ride. So first we were using the SoulSend shifting floors ever since the normal shifting floors got fixed.
Oh, yellow
And
speeds.
they always worked, but the problem was in 1.14 flat, mobs no longer spawned on SoulSend blocks. So basically the rates were cut in half. Like only every second block was a spawnable block. Okay, then we went to the observer trapdoor shifting floor design, which by the way wasn't really a glitch. It was kind of intended way to make a shifting floor. So we just moved this over and then the trapdoor opened and the mob was falling through. So this worked from 1.14
Scottish
flat
accent?
until 1.14.2.
Wait, are you saying this is a Scottish accent? This is definitely German.
Technically it still works, but now we have the issue in 1.14.3 mobs don't spawn on top of those trapdoors anymore, and that would cut the rates of this concept in half. But luckily mobs spawn again on SoulSend, so we can just go back to this design. So the witch farm itself is really efficient. It's a hybrid of a detection system and a clock system. So as soon as a witch would spawn, we would activate those pistons here that would push down an observer, and those would activate the shifting floor, shifts it back and forth. But sometimes that system fails and witches either get stuck between two blocks or don't fall through. That's why we also have a clock running that in case the witch didn't fall through and still is activating the tripwire, so basically it means the observer is down here, would activate the shifting floors again until the witch finally glitches through. Right, yeah, so the system is really efficient.
This
I'm
looks
getting
insane.
4,300 drops per hour with this design.
Whoa.
I also made 2 killing systems again. So the first one was the fall damage system, very easy and very fast. But it has the disadvantage that you can't AFK as high. So in case you would build a double or a quadruple witch shot where you need a perimeter anyway, I would recommend that. But in case you only want to build a single witch farm, then I would recommend actually this anti-crabbing system. So we just flush the witches over to this drop chute, the little one here, and yeah, when they fall down, they're killed by the minecarts that are just standing in there. Also, I optimized
Wait, is this relying on entity cramming as well down here?
it. The witches don't get stuck. They're swiftly flushed over and killed by the minecarts before the witches could despawn. So that's why I'm using the cobble walls here.
Starting to get a little
just
risky.
gives 2 witches enough space to stand next to each other, but we still only need 1 stack of 24 minecarts to kill them. So I can use Master's Mini Hut mod to illustrate that. So this is the despawn sphere around the player. So we got the AFK spot, the single block there in the middle where the player would AFK. And mobs can only spawn or exist within 128 blocks of the player, which is shown by this huge despawn sphere with a radius of 128 blocks.
Camel balloons.
In order to get ideal spawning conditions for your farm, you want the only available space for mobs to exist be inside of your witch farm. So if you look at the bottom here, you got the swamp hut. And if you would put the killing system directly below the farm, we can move the AFK spot higher, and that also means the despawn sphere would also be higher up. So in order to get the ideal spawning conditions, we would just need to light up the blocks that are inside the sphere here. And there's a bit of it underground, we could just maybe dig that away. So it's actually not a lot of blocks. So this would be the advantage of having the anti-cramming system. if we would now build the fall damage system instead, so let me quickly adjust the despawn sphere.
What
We need
next?
to move the AFK spot lower, so about 20 blocks.
Path closed.
And then the area that needs to be prepared would already be a lot
I am
larger.
Quincy, son
So
of
we
Quincy.
would need to make sure that the caves down there are lit up completely in order to get the perfect rates, which you can do by just digging away the area.
Oops, I didn't read what that
But as you
said.
can see, this would be a lot more work. So in case you only have a single witch farm, then I would definitely recommend to use the entity cramming system. But as you can imagine, if you would have a double witch hut farm, then the other witch hut usually is about 200 blocks away, and in order to basically have both of those swamp huts that are about 200 blocks away, or sometimes even more, the AFK spot would need to be in the middle.
This
of
doesn't
both.
seem right. Like this. So we're just doing one witch hut, right? So we could use the entity cramming model. Can I do a Scottish accent? No, Scottish is really hard for me to do. I can't really do accents that great anyway, but a Scottish is Scottish. It's got a lot more. It's like deeper in the throat. But it's really hard to do. Most of I end up going into Irish more. It just ends up becoming Irish. But Scottish, it's very gravelly. Black balloons are small yet contain 2 pinks inside them. Also, black balloons are immune to explosions. Oof. Probably a good idea to have a freezing monkey. Wait, can you move things once you connect? Can you reposition? No, doesn't look like it. Put that there, see how that works. Oh. Only round 21, things are getting a little dicey. Little dicey. Spawn kill? I should probably put something here, huh? I should put something like over here. What would be a good thing to put there? What does this guy do? I'll just see what he does. I don't know what this one is. Exchange bombs for missiles which fire faster, fly faster, and increase range. Okay. These spike guys. I just don't know what this one does. Oh, this is the glue gunner. Nah, that's probably a bad move. This is the one that makes him slow down. Maybe I'll put attack here. Let's try this. Quick shoes are good. Okay, I'll do that next. White balloons are like black balloons but are immune to ice effects. Wait, camel ones can't be affected by your monkeys unless they have a way to detect them. For example, Quincy can level 5 and dart monkeys can with enhance. Okay, we have to be able to detect camo balloons. Quincy? Is that Quincy?
Yes?
Let's see.
What next?
That's pretty good. Purple balloons contain 2 pink balloons and are fast and immune to all energy, fire, and plasma type effects.
Awesome!
Mr. Clean, I wonder if you are stating a hypothetical. Can shoot balloons anywhere it sees on screen with longer servo. Mortar monkey. Man, these things are like, this game is pretty like, there's a lot in this game. Heli pilot. So this is like a man, you have to control this. Let's see. So if I take this, wait, so this doesn't matter where I place it, right? Because I control it. So if I place it, you can upgrade it to auto. So maybe I'll place it. And it just, oh, I move it follows my cursor. Nice. That's cool. Can upgrade it to auto. What's up, Fall Knox? This game is really fun. Yeah, I just got it today. I'm trying it out. Okay, let's see. Let me see how this works. That's cool. That's cool. I like that, actually. That's actually really nice. Little helicopter. Ashi, if you're still here, lead balloons, they're made of metal, so they can't be hurt by sharp things. Try bombs, okay. If you're still here, let me know like when you want to work on the CRISPR stuff. Oh, geez. The heli is a really good tower. It's just expensive, like most of the military towers. Yeah, I mean, I haven't gotten too deep into this game, so I don't know about like the efficiency of each item or each thing. I think so far I'm doing okay. Maybe just put a couple more of these guys in the beginning here. They're pretty cheap. Try to upgrade so it's automatic. Where's the automatic? Pursuit. Oh. A new targeting to seek pursuits automatically. Okay, so you have to get this first. These lead balloons. Maybe I should get more cannons. Sniper. Buccaneer shoots a single heavy dart from both sides of the ship. Must be placed in water. Okay. Monkey sub shoots homing torpy darts at nearby balloons. Must be placed in water. There's no water here, so these are not that useful. Sniping. Ace. Mortar monkey. Sounds good, Fallnox. I'll ask you. Sub is good. But only, yeah, so maybe I won't get that right now. Maybe Mortar Monkey, because it's going to be able to get rid of those lead balloons. Another explosive. I already have like a flying thing. I think I'll go for Mortar. And let's place this one. Man, actually, I don't have like a good spot. I mean, obviously, like that would be a good spot there. Maybe right there. Or actually, this is not bad right here. Camo balloons. Maybe I should work on camo. A lot of monkeys have upgrades that allow them to pop lead, so when you have the XP, you don't need to worry about it. Okay. But the one thing that we do need to think about is camo balloons. So this one can see camo. And then it also said, what did it say? It said something about, wait, these ones being able to see camo? Wait, what does this mean? Close, strong, first. That's the targeting. Nate, I don't have push-ups to do. I finished them last time. If you set it to close, it'll target the closest balloon. Oh, I see. So you can prioritize its targeting. Got it. That makes sense. I think first is fine for right now. I want to look at the upgrades. Quick shots. Where is... Enhanced eyesight. That's what I want. That's what I want, man. That's what I want. The bottom part of the dart allows you to see camo. Bottom pad. Yeah, there it is. I got it. What's up, Kyle? I'm doing good. I hope you're doing good too, dude. Been a while. So I want... Oh, no, wait. Wait. If I closed off this path because I selected... You can only do 2 of the 3 paths. Is that true? So if I go this, and then I go quick shots, you close off, you lock that path. Maybe I'll upgrade to very quick shots too. Got it. Makes sense. Let's see if this works. It's easy street right now. The first camo comes around 24, and then the first leads come at around 29:30. I'm only playing on medium difficulty though, so it's not too bad. Nice. Let's get a sniper. The first Moab? What's Moab? Okay. I'm gonna place the sniper. Oh, wait. It shoots anywhere on the board, right? I already have an attack pilot. Why don't we do... So if the sniper shoots anywhere, why wouldn't I just put it like way over here or something? Like, why would I wouldn't want it close to the path because it's taking up space that I could put something else there that has less range. So if I put this here, just see how that works. I think right now I'm just trying to get a sense of what all these things do. I don't have any particular strategy. I'm just kind of seeing what happens. Warning, camo balloons. More camo balloons on the way. You must prepare your defenses. There are lots of ways to pop camo balloons. Right? Or sniper monkey night vision goggles. Okay. Man, I don't have any XP.
What next?
Attack speed. Bottom path for mortar is not as good. The accuracy stuff. Man, this game is actually way more depth than I thought. Shoots attacks even faster. Actually, what I want to do... Wait, what? Can't upgrade? Oh, oops, I did. That was messed up. That was bad.
What's up?
Okay. Well, I mean, I'm not like that close to losing yet. Seems like I should just keep going until it gets... I'm even getting... Ceramic balloons are covered in a shell of hardened clay and take several hits to pop. Wait, that doesn't look right. Wait, does that thing just literally just fly in a circle around where I placed that? That was a bad place to place it then. Man. What's up, Neil? Hoping you're having a good Saturday. Okay, well, that was a mistake. And you can't move these, right? You have to delete them in order to, or sell them rather, before you can renew them. When you watch people play this game, they will refer to a tower as XXX tower, which refers to the upgrades on that path. The first X being the top path. Oh, yeah. Wow. It's weird. Like the first time I heard about this game was literally like a month ago, but it's been out since 2018. That's crazy. All right, let's do this. These guys are cheap. Oh wow, that was expensive. That was 2000 XP.
Yes?
Oh man.
Incoming! Nice.
Wow. Regrow rainbow balloons. Uh-oh. Oh no.
Seriously?
Okay, well, what was it about that round that made it so much more difficult? What did I mess up there? It's because the balloons were camo. Oh, right. So that was the problem, huh? Oh, I closed the path off for camo. This one can see camo. Oh, I closed these paths. Oh, I don't have XP for that. What should we put on here? Maybe some more. So if a balloon is camoed, Does it stay camoed the entire time, or does the camo disappear if once it gets hit? It stays camoed. Rom, yeah, I did used to play Overwatch, but not like in any like major capacity. I played it for a little bit. It was pretty fun at first, and then I think, I don't know, something happened. I just kind of like lost interest in it. I think at a certain point when it got a little too much, a little too competitive. Oh yeah, maybe. Yeah, I think it was a little while ago. I've been playing mostly Minecraft lately, which has been pretty fun. More chill, more relaxed. Attacks faster, freezes for longer, larger freeze area.
I am Quincy, son of Quincy.
Got a couple snipers for those camo balloons. Have I tried BTD Battles? It's like the online version of this game. Nope, never even heard of it. BTD Battles, the online version. So it's basically a battle. Is it are you going against somebody else in sort of a tower defense kind of style? I have 2,000. I should put in something else. Let's go for a. Let's go for another one of these guys. Over here. Gotta defend against. So you send balloons there, and they defend against theirs. Nice. I honestly, the whole tower defense genre is something that my only reference for it is Plants vs Zombies. From when did Plants vs Zombies even come out? That was like, it must have been a decade ago at least. EA game. That was an EA game. Look at the Wikipedia. 2009. Yeah. Okay. Fair enough. 10 years, almost 12 years ago. The original screenshot. Tower defense. What was the original tower defense game? Whoever came up with the first one. This one? What device is this? Greenhouse, a popular 1982 handheld game by Nintendo. Are you kidding me? Look at this thing. This is a one. Okay, so this is just literally one game in a handheld device. That's his tower. This was a tower defense game. The tower defense genre can trace its lineage back to the golden age of arcade video games in the 1980s. The object of the arcade game Space Invaders. Oh, wait, Space Invaders you could consider a tower defense game? Released in 1978, was to defend the player's territory against waves of incoming enemies. The game featured shields which could be used to stretch. Wow, tower defense is like an OG genre then. Super Kirby Jackson. Ninja gets camo detection when it's first put down. Nice. I mean, Space Invaders doesn't feel like if you remember Space Invaders, right? Like this game, it wasn't really a tower defense because you controlled the tower, right? Because you pressed the button to shoot, right? Am that correct? I feel like Space Invaders is kind of, it's not like exactly. The 1980 game Missile Command changed that by giving shields a more strategic role. In the game, players could obstruct incoming missiles and there were multiple attack paths. (2007 to 2008) boom. Between 2007 and 2008, the genre became a phenomenon due in part to the popularity of tower defense mode in RTS, real-time strategy games, but mainly due to the rise of Adobe Flash and also smartphone app stores. The first standalone browser games emerged in 2007. Among them were the extremely popular titles Flash Element Tower Defense, released in January, Desktop Tower Defense, released in March, Ant Buster. So Plants vs. Zombies was in this sort of, it was like came on the heels of this boom then. Okay. What is this one? Oh, it's like a flash or whatever. Interesting. Well, they've been around for a while, but not to this level, I guess. All right, let's see what we got here. Let's see if this is going to work. That was pretty successful. This one's freezing. Maybe put another one here to freeze more. Oh, I always forget that I oh, this one actually can do that. Closing off those paths. Man, I haven't even unlocked like half of the towers. This game's crazy. This game does not mess around with its strategy or with its like just more slow. It's a commitment to the tower defense genre. Glued balloons pop one layer every few seconds. Let's get some more. Wait, which one was the one that let me get camo? Hold on. Oh, the bottom. Okay.
Nice. What's up?
I actually have not used this thing yet. I don't even know what that button does. So far, pretty straightforward. Oh no. Okay. It's time to upgrade some stuff. Razor rotos. Oh, I forgot to do that. I'm gonna upgrade that.
You want some?
Which ones are the ninja monkeys? The ones that see camo? Do I haven't unlocked them yet? Oh, I haven't unlocked it yet. Uh-oh. What's going on here? These are all camos. I messed up. Didn't have enough camo protection.
Seriously?
It's over. Wait, each balloon is 1 health? Gwendolyn Pyromaniac. Cool. I need more camo defense here. Maybe, wait, this does spy plane is maybe good for camo. I'm really messed up with where I placed this spy plane. What a waste, huh? Maybe I sell it and replace it because that's just bad. Let's put it. I need more. The spy plane doesn't even look like it's doing that good. It's just like too slow. It just doesn't look that effective. Here's the ninja monkey. Finally. Let's put this one. Squeeze him in anywhere around here. Right there is actually not bad. And then let's put another one right over here. Let's put another one over here. These camo balloons are not going to mess me up. Oh no! Oh, that was just straight lost. And those are all camos. And I thought I stacked myself for a camo. Okay. All right. I got to do a little research today. Is there a sea lantern farm on the server? Not that I'm aware of. I don't even know what that is. I doubt it. I haven't heard of it. Heard anyone do it? I mean, I could be wrong. Okay. What are we going to do? All right, so let's go ahead and minimize this for now. All right, Ashi, are you still here? Time to do a little bit of CRISPR stuff. What are sea lanterns useful for? All right, I made a little. I spent like, I don't know, 15 minutes today making a little overlay for when I do research to isolate this. I'm curious to see how this works. So let me try something here. So. See if this works. So this is what it should look like when I want to do some research. Research time. How does that look? Does that look okay? All right, let's see. Does the chat look okay where it is? Let's see. Oh, oops, I messed up with the chat. We need to hide that chat. There we go. Yeah, the chat was just messed up. Okay, that looks pretty good. It doubles as a cod farm, secondary source of food. That's pretty, okay, cool. All right, I think that looks good for research time. I like it. Clean, easy, isolates the chat, isolates my video, isolates the web page that I'll look at. Okay. Give me 1 sec, Ashi. I'm going to use the bathroom and we'll come back and we'll do a little bit of digging here. Can you, Ashi, if you wouldn't mind linking me the article that I had linked you last time, so we can start from there. But I will be right back. Okay. Have some tea going right now, so I'm gonna might go grab some, boiling some water for tea. Okay. So what are we thinking? What are you trying to, are we just trying to get a broad understanding of exactly how it works? Are we trying to look more at like the applications of it, like how it can be used? What do you think? Any preference for like our direction, or you just want to sort of start from the basics of like how it actually works at modifying or editing the DNA at the molecular level? There's a lot of different directions we could take this. Okay. How it's reprogrammed to work and stuff, like how they do that. Okay. So kind of how it's used. Okay. So let's start with just a quick look at this. So this whole first section gene therapy and genome editing, we can kind of skip that because that's just overview. Let me see if I can make this a little bigger for us. There we go. But like mainly, how do the researchers take and manipulate it to do the job? Okay, fair enough. So basically, how it's used to edit DNA. So like if the researchers, they want to, let's say, edit a certain sequence of DNA in a person, how do they program the Cas9 and to go in and do that? Okay. Within the past 5 years, a completely novel system has been developed based on fundamental research on bacterial systems of immunity to viral infections. The first such system to be developed for use in genome editing of human cells, known as CRISPR-Cas9, is based on RNA-guided targeting and is much simpler, faster, and cheaper than earlier methods. The ease of design, together with the remarkable specificity and efficiency of the CRISPR-Cas9 system, has revolutionized the field of genome editing and reignited interest in the potential for editing the human genome. The development of CRISPR-Cas9 system as a programmable genome editing tool was built on a firm foundation of earlier research. Let's look at this real quick. When did this come out? 2017. Okay, this is three or 4 years old. Breakage and repair of genomic DNA. So genomic meaning DNA in the genome of an organism. So genomes and their constituent genes are made of double-stranded DNA, right? Very basic. This DNA can be broken accidentally. What up, Doom Kaiser? Can be broken accidentally, for example, by radiation, or purposefully by using proteins called endonucleases, often called nucleases, that can generate double-stranded breaks. Cells have mechanisms to repair. These mechanisms can be used to generate alterations in the DNA sequence. Groundbreaking work in bacteria, yeast, and mammalian systems show that double-stranded breaks dramatically stimulate the rate of DNA repair by non-homologous end joining, in which the broken strands are reattached. Okay. However, if a homologous stretch of DNA, by the way, if you have any questions as I go through this, like you're like, what does that mean? Please let me know. I'll try to explain things if I think they need to be explained, but I might miss something. All right. If a homologous stretch of DNA is introduced into the cell as a donor template, homology-directed repair can lead to a more accurate repair of it. If specific alterations are included in the homologous stretch, it can introduce specific, precise changes into the recipient genomic DNA. These cellular DNA repair mechanisms have been used to develop several methods that allow genes or the genome to be edited in a very precise manner. Okay, so this looks like a little bit of older tech. That you can't see that. Sorry, something I had popped up in an image. It's not showing up. Let me. So I was just looking at this image here. So you have a break in the DNA due to radiation or maybe a nuclease induced. So this is an enzyme that breaks a double-stranded break. So it breaks both strands of the DNA. there's two types of repair. There's this NHEJ, which is non-homologous end joining. And then there's the HDR, homology-directed repair. Okay, I don't think we really care about this because it's not particularly directly connected to this. So there are precursors. Okay, let's not worry about the precursors. Here we go. This is what we care about. The development of CRISPR-Cas9. One sec, my tea's ready. Okay. Okay, the discovery that CRISPR systems provide adaptive immunity to bacteria. We already know this. Discovery. CRISPR loci were first identified based on analysis of bacterial genomes. From these studies, it was inferred that the spacer, i.e., non-repetitive regions of CRISPR loci were derived from the genomic DNA of bacteriophages, viruses that infect bacteria, leading to the hypothesis that CRISPR provided a defense mechanism against foreign genetic elements. So this was back in 2005. So we see a couple of peer-reviewed articles here that are describing this hypothesis that they had found that these sequences, loci, by the way, means location on a chromosome or in the genome. So the idea is that in these bacteria genomes that these people were studying, they found these places in the bacteria's genome that had sequences of DNA from viruses that had attacked these bacteria. And so they were somehow storing the viral DNA in their own genome. And that's what the CRISPR, so that's what CRISPR is. CRISPR is the actual stored viral DNA in the bacteria. And so they hypothesized that it was a defense mechanism against foreign genetic elements. The key experimental breakthrough came from research showing that CRISPR allowed bacteria to acquire resistance to bacteriophages by integrating segments of the bacteriophage genome into the CRISPR loci, demonstrating that CRISPR was a new form of adaptive immunity. That was in 2007. In 2010, type 2 CRISPR/Cas systems were shown to mediate cleavage of invading bacteriophage DNA. And in 2011, an associated RNA, tracer RNA, was identified. And the CRISPR-associated gene, Cas9, was shown to be the only protein-coding gene in the type 2 Cas locus required for the defense function. That was 2011. Okay. So by 2011, these researchers had sort of established that the Cas9 protein was all you needed to activate this sort of defense mechanism associated with CRISPR. So, development of Cas9 as a programmable endonuclease. The critical advance in the development of the CRISPR-Cas9 based genome editing method came in 2012 from the laboratories of Doudna and Charpentier. So I don't know that. They established that the CRISPR-associated protein, Cas9, in complex with two small RNAs, CRISPR RNA, transcribed from the CRISPR locus, and a transactivating RNA, yields a site-specific endonuclease. So a site-specific meaning like very particular, right? Like specific to a very particular place in the DNA. Endonuclease, which is an enzyme that can cut DNA out, in which the site of cleavage is defined by base pairing of the CRRNA to the target DNA. So basically, the CRISPR RNA, or the CRRNA, base pairs with the target DNA, and then that is what shows the endonuclease where to cut. So you have this like template RNA, which would base pair with the DNA, like complementary base pair would match, and then that tells the endonuclease cut here, basically. This laid the groundwork for establishing that Cas9 is an endonuclease that can be programmed with a single guide RNA. And the guide RNA, which is the GR, stands for gRNA, is a chimera. A chimera is a blend or a mix, I believe, if I remember that term correctly. Chimera. Okay, it's definitely not a fire-breathing female monster with a lion's head, a goat's body, and a serpent's tail. Genetics here. Genetic chimerism or chimera is a single organism composed of cells with more than one distinct genotype. Yeah, basically a chimera is like when you mix together things. So it's a chimera of the CRISPR RNA and the tracer RNA. So it's kind of a mix of the transactivating RNA and the CRISPR RNA. That is what gives you this guide RNA. So they're kind of combining the two pieces of RNA that are required to guide Cas9 to the location to cut the DNA. Right, so that would allow the Cas9 to cleave at a specific DNA site. That was 2012. Concurrent with the GENIC 2012 manuscript, CRISPR and co-workers demonstrated that purified complexes containing Cas9 and a CRRNA could mediate cleavage of double-stranded DNA in vitro. In vitro means outside of the body, outside of an organism. So like in a lab environment, in like a test tube or a petri dish or something. Could mediate cleavage of double-stranded DNA in vitro at sites complementary to the CRRNA. Okay, again, straightforward. The CRRNA is that CRISPR RNA. That is what is going to be complementary to the location in the DNA that has the site that we want to cleave. While this was clearly an important advance, a key missing element was the identification of the requirement for the tracer RNA to form an active endonuclease. Let's look at this graph a little bit. So this is the Cas9, which is this yellow blob. This is the enzyme. That's actually this is the endonuclease enzyme, the Cas9, that's going to do the cutting. The guide RNA is this strand here that has a complementary section, apparently. and then the Cas9 is going to cut there. Yeah, it seems that's the case. It seems like, based off what this is saying, is that normally, like in a bacteria, right? So this is what we're saying right here in the beginning. Right here. This is the important part. So in 2012, there was a critical advancement where they established that the CRISPR-associated protein, Cas9, that's what's CRISPR-associated protein, Cas9, is in complex with two small RNAs, the CRISPR RNA and this trans-activating CRISPR RNA, or tracer, yields a site-specific endonuclease in which the cleavage is defined by the base pairing of the CRISPR RNA to the target DNA. So it sounds like you've got the CRISPR RNA and then this trans-activating RNA or tracer RNA that together sort of guide Cas9 to the correct location to cut the DNA. And then the guide RNA is a combination of the CRISPR RNA and the tracer RNA. But apparently there's a key missing element was the identification of the requirement for the tracer RNA to form an active endonuclease. So I guess they still don't, at this point, right, they still don't quite understand why the tracer RNA is important, maybe, in activating the endonuclease to do its job. So let's see what they say. The 2012 paper made the key breakthrough of the use of a single chimeric guide RNA that can fulfill the role of both the CRRNA and the tracer RNA. Thus, mechanistically, the CRISPR-Cas9 system is superior. I don't know what these are. To both this is zinc finger nuclease. These are the old, outdated versions. These are from back up here. Yeah. These are older methods, zinc finger nuclease, other ways of cleaving DNA. In terms of ease of use, all that is required to generate a site-specific nuclease is design and synthesis of a single guide RNA to target the Cas9 nuclease to the desired site of editing. Although not all predicted guide RNAs work, their synthesis is easy and multiple possible candidates can be synthesized easily and cheaply. So this is the in vivo application is basically getting at, now, what about in the body, not outside? In vitro is like outside of the body. In vivo is in a living organism. Okay, within months of the publication of this 2012 manuscript, there were 6 independent reports using the Cas9 guide RNA system to mediate programmable genome editing in vivo. These included 4 papers reporting Cas9 editing in mammalian cells, 1 in a zebrafish, 1 in a bacteria. Additionally, there was a 7th paper showing that dCas9 could be used to inhibit transcription. Since that time, there has been an explosion in the application and refinement of Cas9-mediated cleavage, as well as the discovery of novel CRISPR systems that can be adapted for genome editing. These include the discovery of a novel RNA-guided endonuclease, and more recent work has been shown that further CRISPR targeted nucleases with the potential for different capabilities are being discovered. Okay. So it seems like this enzyme Cas9, this endonuclease, all you have to do is feed it a guide RNA or a gRNA that you have created. So we are able to create sequences of RNA. We can make RNA in the lab. So imagine that so let's just say, 1 second, let me pull up. Okay, there we go. That's what I was trying to get. So kind of just to sort of put a picture to it, right? Like if you've got a DNA, so imagine you've got like a DNA molecule. Boom, 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 boom. We'll just do like a very basic. What you can do, and we have the ability to do this, is we can sequence, right, with genetic testing and genomics. We have the ability to take DNA from an organism, extract it, and sequence it, and figure out what the order of the letters are. This is just technology that exists. It's been around for a while now. We can do this. So let's say that there's let's say there's a gene right here, okay, that we want to get rid of because we just don't want it for whatever reason. It's probably not really that often, but let's just say that. And it's let's say A, C, T, G, A, C, T, G, A, C, T. Oh, went too far. Just say it stops right there. Okay, so that's the gene that we want to get rid of. If we want to cut this out, all we have to do is sequence the RNA version of this, and probably has to be slightly modified. It probably has to have like a piece. So the CRISPR, the CRRNA that we talked about before. So we'll say the CRRNA would be a single strand of RNA with and it would just be the opposite, right? It would be the complementary to this strand of DNA. So it would be A would pair with a U, C to a G, T to A, G to C, A to U, C to G, T to A, G to C, and A to U. So this would be the CRISPR RNA. Now, I don't really understand the tracer RNA. I don't know. But there's a second small piece of RNA that has to go along with the actual complementary base that helps helps direct the Cas9 in some way that I don't know. But the idea is that people have taken these two things, right, and combined them into something called a gRNA, which is the guide RNA, which takes the complementary sequence here plus this other sequence and gives you the guide RNA. That guide RNA is then going to help direct Cas9 to this site to cut it out, right? And so Cas9 is going to use the guide RNA to remove the sequence. So that's where we're at right now. So is that answering your first initial question, Ashi? This idea of like, how do you reprogram Cas9? You basically just make a new gRNA with the sequence that you care about that matches that's the complementary sequence to what you're trying to cut out. So the guide RNA is RNA matching the trait they don't want, so they take it out. Well, to an extent, right? So it's matching, the guide RNA is matching the sequence of the DNA, right? And so this would just be cutting it out. Now, the question is, how do you go in, what's the next step would be, right? Let's just imagine like the most simplest form of like a gene that has a mutation in it that's causing a disorder. We don't want to cut the entire gene out, because if you'd remove an entire gene, that's not good. You want to fix the gene. So you want to like somehow be able to switch some of the letters of the bases, like turn a G into a C or an A into a T or something like that. Now that maybe we have to read a little bit more to figure out exactly how do you use CRISPR-Cas9 to not just cut something out, but cut something out and put something in its place, right? So you could imagine, let's say that thanks for the sub. Shrutik, what's up? Are you the Shrutik that I know? Much appreciated, dude. Give me your Prime, your Amazon Prime. So let's think about this in the sense of one. Let's just say, most simple. There's one letter. This A. I'm gonna make it in red. This A is a mutation. This should be a T. So what we would want to do is be able to program CRISPR to simply go into here, cut the A out, and replace it with a T to fix this mutated gene that's causing some disorder. That's what our goal would be. So now we kind of understand how you would guide the Cas9 to this area simply by creating a sequence of cRNA and this tracer RNA that this, again, yeah, I think this is something that I don't quite understand. But either way, like you generate this and you get this gRNA that then basically guides the Cas9 to this location, and the goal would be to get the A to be removed and replaced with the T. So I think we have to read a little bit more to get into how does it edit it in such a perfect way. Because obviously we don't want to just cut and delete an entire gene out. So let's see. Accuracy of gene editing. Okay, the potential impact of unintended changes to DNA is a key challenge for safe use of genome editing as a therapeutic strategy. Unintended changes to the genome could be caused by cleaving DNA at sites other than those that are being deliberately targeted, right? So like if I wanted to go in and change that A, I have to make sure that my Cas9 is cutting the A at only that location in the entire genome. Because if it's cutting it anywhere else, you're getting a lot of problems, right? Because now you're messing with other genes that we don't know what they're doing. Thanks for the follow, dumb joke. So yeah, that's the idea. So let's go a little bit further here. Ashi, how much do you care about learning about the accuracy piece? Well, maybe it's important to read. Challenge of off-target toxicity. Do the researchers take the Cas9 from bacteria cells and then insert it into eukaryotes when inserting the guide RNA? Okay, well, that I don't know. That we have to read a little bit more. So like the idea of how, I think I remember you asking, you were interested in like, what are they actually injecting right into the person, right? So imagine that you're a person with this disorder and you're trying to get treated. What are they administering to you? Like, are they just injecting something into you that is a mixture of the guide RNA and the Cas9? Like, how does that work? Yeah, that's a good question. So let's look down. Given its ease of use, flexibility, and versatility, the CRISPR-Cas9 system is rapidly becoming the tool of choice for gene editing. However, concerns about the potential risk of unwanted off-target effects have dominated many recent discussions. Most experiments that have detected significant off-targets have been performed in cancer cells, which may have altered DNA repair pathways that could lead to elevated off-target events. In contrast, experiments in whole organisms such as mice, primates, zebrafish, or C. elegans reported off-target frequencies that were low or not detectable, consistent with the high specificity of the CRISPR-Cas9 mediated gene targeting. It is possible in non-transformed cells, off-target cleavages are efficiently counter-selected by the endogenous DNA damage repair response. So maybe if there's an off-target cleavage, right, like meaning like it's a mess, it doesn't do what you want it to do, or it does it somewhere else. That endogenous means already present inside of the cell, right? Endogenous. So you have your own, so within our own cells, we have DNA damage responses. So it could be that even if CRISPR-Cas9 does a cleavage somewhere where it's not supposed to, our cells have a built-in response that can fix that for us. So maybe that's what that's saying. Let me see. The challenge of delivery. So here it is. General approaches to delivering genome editing components. So these are some approaches with how do we deliver or give this CRISPR-Cas9 to a person. So these are non-viral. So, oops, I messed that up. Okay, so non-viral methods. Transfection. The guide RNA is plasmid DNA or oligonucleotide is mixed with nuclease RNA. All components are assembled with a glyco/lipopolymer vehicle that favors cell entry. The complex is applied to cells ex vivo or injected into a tissue or blood in vivo. Advantages: relatively simple, can deliver all editing machinery together. When it says all editing machinery, I'm assuming it means the Cas9 endonuclease enzyme as well as the guide RNA and maybe some other components. The disadvantages: cellular uptake and nuclear access can be rate limiting, which means it might be slow. Vehicle can cause cytotoxicity and inflammation in vivo. Okay, so that's not good, inflammation. For the in vivo delivery of RNA needs to be modified for improved stability, cannot be targeted to specific tissues. Preferred application: cell lines and some primary cells ex vivo, so not in the body. Nanoparticles, which would help uptake. Electroporation, a brief electrical pulse is passed across a population of cells. So this looks ex vivo. So these are things that are not done in the body. So this would be like cells that you've taken out of the body and are working on. Microinjection are used on zygotes and early embryos. So basically, it's just like you just literally inject it in a salt solution, a saline buffer, which is like saline buffer is like sort of a salt solution that is sort of meant to match cell cytoplasm. So the viral ones, so this would be like viral vectors, right? Where you're putting all of the components you care about into a virus, and then that virus is injected into the person, and then the virus itself goes and delivers the stuff into the cells. So let's see. Nucleases and guide RNAs as gene expression cassettes delivered by the vector genome. This is currently the most common tool for ex vivo gene transfer and also being explored for in vivo use. Template DNA can be used for the delivery of the template alone. In combination with electroporation, adeno-associated virus vector. Primary cells, ex vivo and tissues or systemic in vivo. So this packs DNA. Currently the most common tool for gene transfer in vivo. Remains mostly episomal in the target cell nucleus. What is episomal? Episomal, a segment of DNA in certain cells, especially bacterial cells, that can exist either autonomously in the cytoplasm or as part of a chromosome. Okay, so it's just like a section of DNA. So it looks to me that the way they do this is they basically, right now, if they're trying to do it in vivo, meaning a living organism, they inject it's a viral vector. So what they basically do is they inject, they basically engineer a virus. They take out the viral DNA and they put inside the virus the DNA that will code for both the Cas9 nuclease and the guide RNA. That once it's injected into the cell will start to make the Cas9 protein itself through protein synthesis, and the guide RNA will be there as well and be created, and then the Cas9 will use the guide RNA and then go and do the edit. Okay. So what's interesting here is it seems like they literally have a 2-sentence part on the delivery, right? So we might need to go and find another source for that, because most of this is about stuff that's a little not directly related to what we care about. Let's see what this is. So it looks like here's a good image of basically all of the different kinds of gene editing things, but you can kind of see they have a scale here of feasibility from left to right of like being able to probably be used in for like any therapeutic value. And you can kind of see that CRISPR-Cas9 system is way over here on the far end of the feasibility scale. And you've got like these other like things like zinc finger nucleases that we saw before that don't seem to be as relevant. Blue, what's up, my dude? Long time no see. How goes it? You still playing CS? Nah. What have you been up to? Ooh. Playing some League. With League of Legends, there's so many characters, right? There's what, 150 or so characters, and they like release, they release a few characters every year. How does that even make sense? It seems so like for someone who's just starting a game like that, and it's like pick your character, and there's like of 150. It just seems so overwhelming. Like, how do I even pick? You got more schoolwork to do because winter course startup. Okay. Back to the grind. The schoolwork grind. Oh, you unlock them as you go. Okay. I feel like I would just want to pick one and get good at that one. It feels like it'd be hard to get good at more than one. It is just to pick one and go. Yeah, I've been considering picking up. I've been doing a lot of Minecraft lately. It's pretty much the only game I've been playing for the last probably couple months. But then I was watching Len play some Valorant earlier this week, and it looked pretty fun. So Valorant is a game that I've been considering playing, but League of Legends is one that is another thought of maybe a little more of a fast-paced game just to try it. Have you played Valorant? Seems good. 5 maps, yeah. But wait, in League of Legends, there's only one, right? It's the same map every time? Or is that wrong? Yeah. Okay. So interesting. Okay, evolution of second generation CRISPR gene editing tools. This is kind of cool. Valorant's a little difficult to learn. Well, I've been told that Valorant is kind of like or at least this is what Len said. He was like, it's all of the best games combined. I forget exactly how he phrased it. Maybe like a little bit of a mix of Counter-Strike and Overwatch, right? Isn't that kind of what it's been deemed as? Overnight Fort Watch and CO all went to Valorant. Yeah, makes sense. Do you think it is the next big thing? It's been out for a while though. I don't follow esports that much. Like insofar as like what's got all the big money prizes right now? Like where's all the money going? Like, for a while it was definitely it seemed like Fortnite had a lot of big tournaments, but now it's kind of fallen off. Yeah. Ashi, what's immunoprecipitation? That was somewhere above. You scrolled past it. Immunoprecipitation. Immunoprecipitation. There's only this one right here. Immunoprecipitation is the technique of precipitating a protein antigen out of a solution using an antibody that specifically binds to that particular protein. This process can be used to isolate and concentrate a particular protein from a sample containing. Okay, so basically, antibodies bind to specific proteins called antigens. So an antibody will match with an antigen, right? So each antibody is very, very specific to a specific antigen. And when it binds, it will like precipitate, which means it comes out of the solution into like a solid that sort of can sink to the bottom of the solution. So for example, if there's a protein that's dissolved in a solution that you want to get out, apparently immunoprecipitation is a way of putting antibodies into the solution that bind to that protein and then pull it out of solution. Exactly, yeah. Pretty much, yeah. So when that is a form of clotting. So if you get, for example, like if you get the wrong blood transfusion, right? We talked about this last semester rather. If you get injected with blood cells that carry an antigen that is not your own, your immune system will attack it. So the antibody will clump on, will bind to that antigen and clump, and that causes the blood clots that are so deadly if you get an improper transfusion. So I'm not 100% sure how they're using this in this. Where was it? Over here. Re-engineering. Yeah, so I guess it's just a technique for getting proteins out of solution by using antibodies. I was a section down here. Doom Kaiser, what's your rank in League? Gold 2. What are the ranks? Are the ranks similar to StarCraft ranks? Like in terms of the levels, like bronze, silver, gold, platinum, diamond, master, grandmaster. That's the StarCraft ones. Iron, bronze, silver, plat, diamond, master, grandmaster. Okay. So the only difference is that there's an iron. There's an iron level. League is super bottom heavy. Let's see. Let's see if we can find a good video to help us sort of summarize this to make sure we have the right idea here. 80% of player base is gold 4 and below. Dang, you're gold 2 and you're in the top 15. Nice. I was never good at competitive games. Okay, let's see if this gives us any info.
Shortly after its discovery, the CRISPR-Cas9 system has taken the world of gene editing by storm. The CRISPR-Cas9 system has become the go-to technique when it...
Okay, here, look at this diagram. Cas9 is this sort of tan blob behind everything. Target DNA, target sequence, and then your guide RNA. Okay.
It comes to mutating and editing DNA in life science research. The beauty of CRISPR-Cas9 system is that it only requires 2 components: a Cas9 enzyme to snip target DNA, and an RNA molecule called the single-strand guide RNA that directs the Cas9 enzyme to the precise spot through complementary DNA pairing. In our previous video, we introduced the CRISPR-Cas9 system briefly. Here, we will go over the methods and tools available to you for using the CRISPR-Cas9 system in practice. We invite you to watch our previous video first before continuing with this one. Genome editing is achieved once the 2 components of the CRISPR-Cas9 system have been expressed in living cells.
Expressed in living cells. Okay, so that means that somehow your cell has to make the guide RNA and the Cas9 through protein synthesis. Well, this would be protein synthesis to make the Cas9 enzyme. The guide RNA would be expressed through transcription only, right? Because you're making the RNA. But both of these would have some sort of gene, DNA gene, that would have to be inserted into the cell's DNA, potentially, or it could be like yeah, probably into the DNA. Yeah, and then the cell would make these things.
The delivery efficiency of the Cas9 endonuclease along with the gRNA directly affects the successfulness of genome editing. There are several methods to express these components in living cells, either through non-viral or viral gene delivery systems. There are two common non-viral gene delivery procedures available. One, chemical methods such as lipid-mediated.
Wait, so it's that researchers make something that then codes for the gRNA and Cas9? It seems to be. It seems that way. It seems like that. And that's yeah. So like they'll make the instructions for the guide RNA and the Cas9. They'll make the instructions for it, and then those instructions get delivered into your cells. And then your cells take those instructions and make the guide RNA and the Cas9 in the cell, and then they get activated, and then they go and change the DNA that you care about changing. And that, by the way, that's the same way that the COVID vaccine is working right now. So right now, if you go and get the Moderna or the Pfizer vaccine, these are mRNA vaccines. And so what they're doing is they're injecting messenger RNA, which is just the instructions, the RNA instructions, for making the spike protein that exists on the SARS-CoV-2 virus. That spike protein is an antigen that your body then recognizes and makes antibodies for, so that when you get COVID-19, you fight it. Your immune system has already recognized it and is ready to attack it so that you don't get sick. Now, of course, we learned previously that these vaccines don't necessarily protect you from being contagious to other people, because you can still get infected and be contagious, asymptomatically contagious, but it prevents you from getting symptoms potentially, or that's the idea. 95% effective at preventing the symptoms, so you don't get sick and die. So apparently there's multiple ways for this to be delivered. So let's see, there's non-viral and then there's viral. So the chemical methods are here.
Transfection, or calcium phosphate transfection. 2. Physical methods including electroporation or laser-mediated transfection. Lipid-mediated transfection involves the use of cationic lipids or cationic polymers. First, the negatively charged phosphates of the DNA backbone associate with these positively charged lipids or polymers, forming a complex called liposome. The liposomes, which are essentially vesicles containing the exogenous DNA, can then merge with the cell membrane.
Okay. So you've got a little... Remember we talked about vesicles? I don't remember when we talked about them, but like last semester, a vesicle is a little bubble of lipids, and inside is the exogenous DNA, which is exogenous meaning from another place, DNA from another place. So not DNA from the inside of the cell. Wait, so this would be the instructions for making Cas9 and the guide RNA. So you kind of package the instructions in this little bubble of lipids, and then almost through endocytosis, this little bubble fuses with the outside membrane of the cell and releases it into the cell.
And release their content inside the cytoplasm. Yeah. The advantage of applying lipid-mediated transfection is its high efficiency in a broad range of cell lines. However, that efficiency depends on the optimization of culture conditions of each cell type. The principle of calcium phosphate transfection...
I don't think you would use that last method in vivo. I don't know, maybe you could. I'm not sure.
Involves mixing the DNA with calcium phosphate to condense the DNA and form a calcium phosphate DNA coprecipitate. The calcium phosphate also helps in binding to cell surface, and from there, the DNA enters the cell by endocytosis. Calcium phosphate transfection has been a common method since the early 1970s due to its inexpensive components that are readily available. Depending on the cell type, calcium phosphate may not be a suitable transfection method as it can have cytotoxic effects. In addition, reagent consistency such as a small change in pH can result in compromised transfection efficiency. Electroporation. As the name suggests, this method uses an electrical pulse to physically create temporary pores in cell membranes to allow foreign DNA to enter the cells. This method allows various types of DNA to be introduced readily into cells without limitations of DNA size. On the other hand, the main concern with this method is the substantial cell death caused by the high voltage pulses. The use of this method requires more cell numbers compared to chemical transfection methods. While the non-viral methods mentioned are generally sufficient to deliver foreign genes into cells, most of the time they are transient expressions and the efficiency can be low depending on the cell type. In order to maintain gene expression with high gene delivery efficiency, viruses are still the preferred system for many researchers. There are 3 types of viruses commonly used for gene delivery in living cells. These include lentivirus, adenovirus, and adeno-associated virus. All 3 types of viruses are required to be modified into replication deficit viruses in order to be applicable for gene delivery. Lentiviruses are single-stranded RNA viruses belonging to the Retroviridae family. Lentiviruses enters the cells through the interaction of viral envelope protein and cell surface receptors. Once inside, they will stably integrate their genome to host cell chromosomes. Long-term transgene expression is thus achieved in target cells, which provides a major advantage to gene expression researches. Adenoviruses are well-characterized, non-integrating linear double-stranded DNA viruses that enter target cells via receptor-mediated endocytosis. They are known for their outstanding delivery capacity of foreign DNA fragments up to 36 kilobases, as well as their ability to give almost 100% transduction rates on many dividing and non-dividing cell types. Instead of combining its own DNA with the genome of the host cell, adenoviruses remain as an episome within the affected cells, giving transient gene expression. One important thing to note about adenoviruses is that they tend to cause strong immune and inflammatory responses among animal models. Amongst all recombinant viruses, adeno-associated viruses, also known as AAV, is the most promising candidate for gene therapy owing to its 2 properties: non-integrating nature and the lack of pathogenicity in animal models. AAV is also a very attractive tool in regenerative medicine due to its differential tropism that can be achieved with different AAV serotypes. For instance, AAV2 presents natural tropism only towards skeletal muscles, neurons, and hepatocytes.
Okay, so it seems like this is the adeno-associated virus AAVs look to be like the pretty good because one is they don't generate a huge immune response, and you can target them to specific tissues based off of the version of the AAV, right? So if you use like AAV2, it'll go for the central nervous system or your eye retina and liver and muscle. But something like AAV5 will not go to the muscle and instead go to the lung tissue. So it's kind of like specific to different tissues, which might be good if you're trying to alter a gene in specific areas of the body.
The downside of AAV application is its naturally small genome size, restricting its cloning capacity. The viruses offer a very simple procedure to gene delivery, allowing for high efficiency transcription.
Okay, so just to kind of give you a brief understanding of this table, packaging capacity, this stands for kilobases, so thousands of bases, so how long the DNA strand can be. So you can see like the adenovirus can hold the most DNA, 8 to 9,000 bases, whereas the AAV only 3.4 thousand. So it's not that long. Efficiency, this is just, I guess, a rating of stars. Cell type, integrating, yes, no, 90% not, 10% may integrate. And then immune response, how much your immune system reacts to it. So it's clearly that adenoviruses, your immune system have a response, which is why it can be inflammatory to your body.
In both proliferating and quiescent cells. These viruses are often technically challenging and laborly intensive to produce.
Creepy, what up, my dude?
Efficient delivery of the Cas9 and gRNA into a living cell is required to carry out genome editing. ABM features Cas9 expression tools in the form of plasmid vectors, proteins, lentiviruses, adenoviruses, and AAVs. In addition to the wild-type Cas9 nuclease,
This guy, good meme,
ABM
dude.
also provides the Cas9 nickase in all formats. So depending on your application,
I heard you had some qualms with the witch farm that we built yesterday. I took a brief look at the video that you recommended, and it was definitely more complicated. So it looked right up your alley. That looked more of a creepy farm.
you can choose the best expression system for your research project. ABM also offers genome-wide sgRNA library ready for you to use. We provide individual lentivirus construct in a set of 3, which will provide you 3 different sgRNA designs targeting different locations of your interested gene. They can be used separately or pulled together to achieve optimal gene knockout for your system. Similarly, our iCRISPR sgRNA adenoviruses and AAVs are useful for non-integrating, highly efficient genome editing in hard-to-transduct target cells. Although Cas9 and gRNA can be expressed from separate plasmids.
Okay, this is getting a little technical at this point. We don't really need to go into this level of detail. CRISPR Cas9 gRNA design. Okay, so you think you could potentially modify the one that we made to make it more efficient? Oh, another question that I had for you was, does your gold farm that you built rely on increased entity cramming? Does that affect it? Because if not, we don't need to have entity cramming at 250. It doesn't? But what about all those piglins that fall? Don't they get all, wouldn't they start dying if they reach too many in one spot? Or would it just be the fact that you wouldn't AFK there too long? You just allow them to fall and kill them as they're falling. They are in honey, so their collision is disabled. Oh. Their collision is disabled. So you can get rid of, so you can avoid issues with entity cramming simply by putting mobs into honey? Yeah, I noticed that. I noticed that farm is absolutely not an AFK farm. Like, there's no need. You can literally go there and like get out in like within a minute and have plenty of XP. Okay. Ashi, what anything else that you're still confused about? or that you want to research more about here, you can watch this other video about the designing the guide RNA if you care about that.
The RNA-guided CRISPR-Cas9 system has revolutionized genetic engineering by allowing targeted genomic modification through the simple design of a 20 base pair guiding sequence. This groundbreaking technology utilizes a short guide RNA, sgRNA, to direct the Cas9 nuclease to a specific genomic locus through complementary base pairing. The guide RNA, or sgRNA, is responsible for the specificity of the CRISPR-Cas9 system, and many considerations need to be taken during its design process. In our previous videos,
Cool.
we
Thanks,
introduced
good.
the CRISPR-Cas9 system briefly.
Always
and presented
appreciated,
the different
Creepy.
tools and methods available for their expression in living systems. Here we will go over the design criteria of the gRNA, introduce you to the online programs that simplify this procedure. We invite you to watch our previous videos first before continuing with this one. In bacteria and archaea, the CRISPR RNA, cRNA, and transactivating CRISPR RNA, tracer RNA, form a complex which acts as the homing device for directing the Cas9 nuclease to the invading foreign genetic materials. The tracer RNA's scaffolding ability along with the specificity of the cRNA can be combined into a single synthetic gRNA, simplifying guiding of targeted gene alterations to only a one-component system, all while maintaining equal or higher efficiency.
Okay. So that kind of explains the idea that we were talking about earlier.
The targeting specificity of the CRISPR-Cas9 system is determined by the 20 nucleotide sequence at the 5' end of the gRNA. For the S-pyogenese CRISPR-Cas9 system, the desired target sequence must immediately precede a 5' NGG protospacer adjacent motif, or PAM. The gRNA base pairs of the complementary strand.
How do those viruses help with Cas9? Well, the viruses would be carrying the instructions for making the Cas9. So let's imagine so here's the way it kind of works. So let's say here's our cell that we want to edit, right? And so here's our nucleus. A virus is going to basically look kind of like this. This will be, let's say this is the AAV, the adeno-associated virus. Inside, you have DNA. This is the instructions. Whoops. This would be like okay. So this is a sequence of DNA that you've created in the lab that has the instructions for how to make the Cas9 enzyme and the guide RNA, which are the two components that you need to edit the DNA in the nucleus, right? So what this does, once you inject this virus into a person, let's say, this DNA gets injected, right, into the cell, right? And now you've got those instructions in the cell. And along comes if this is DNA, it's going to have to go, and it's going to have to make its way into the nucleus so that it can be transcribed and translated. But if this is RNA, like mRNA, then it could just be grabbed on by a ribosome and can be used to make the Cas9 and the guide RNA, which then combine to edit the DNA. Does that make sense? I'm gonna use the bathroom real quick. Be right back. Yeah, exactly. Yep, exactly.
Of the target sequence where the Cas9 nuclease mediates a double-strand break, around 3 nucleotides upstream of the PAM sequence. Note that the PAM sequence is not part of the 20 base pair gRNA sequence. However, its presence in the genomic DNA is essential for CRISPR-Cas9 genome editing. There are 3 points to consider when designing your gRNA which relate to the sequence of the 20 base pairs guiding sequence. 1. GC content. The typical range is between 40 to 80% GC content. A higher GC content stabilizes the RNA-DNA duplex while destabilizing off-target hybridization. 2. Length. The length could be adjusted and range from 17 to 24 base pairs. A shorter sequence leads to minimized off-target effects. 17 base pairs is the lowest limit on the length of the guiding sequence. Any sequence shorter than 17 has a statistical chance of targeting multiple genomic loci. 3. Potential off-target effects. Mismatch tolerance between the gRNA and target site is what leads to off-target effects of the CRISPR-Cas9 system, and in general, they depend on 1. Position of the mismatch, 2. Number of mismatches in any given gRNA, 3. The sequence of the guide RNA, and 4. Concentration of the gRNA and Cas9 transfected. For the purpose of creating a small indel mutation through non-homologous end joining, there are many possible target sites across any protein. Targeting closer to the end terminus of a protein coding region is more desirable, because a frame shift is more likely.
All right, this is getting a little bit into the technical of like literally like a tutorial of like how to make a guide RNA if you want to, which we don't really care about that level of detail because we're not going out and actually making one. So hey, let's watch this one.
My name is Neville Sanjana. I'm a biologist at New York University and the New York Genome Center, and I've been challenged today to teach one concept in 5 levels of increasing complexity. My topic is CRISPR. CRISPR is a new area of biomedical science that enables gene editing, and it's helping us understand the genetic basis of many diseases.
So after all that research we just did, Ashi, let's see what level we were at. What level were we at? The level 1 through 5. I'm gonna guess we were at level 4.
Diseases like autism or cancer.
What are your
I think
results,
today,
Creepy?
everyone can leave with understanding something about CRISPR at some level. Hey Tegan, do you know what we're here to talk about today?
Science.
We are here to talk about science. We're here to talk about something called CRISPR. Have you heard of that?
No.
CRISPR is a tool that scientists are using to edit or change genomes. Do you know what a genome is?
No.
It's kind of like an instruction manual. The instruction manual that makes you who you are. Sometimes there's mistakes in the instruction manual, like people get sick.
Like allergies?
Like allergies.
Kid is so
Do
cute.
you have friends at school that have allergies?
He's got a little crossed eye in his
I have
bow tie.
Penicillin and azithromycin. They're a type of medicine.
It's good
Wow.
that you actually know
You know
exactly
what
what you're allergic to.
erythromycin
For
is.
people that have really severe allergies, we could erase where in that big instruction manual where they have those allergies, and maybe make it so that they don't have those allergies anymore.
Blowing my mind.
Do you know what CRISPR is?
Absolutely not.
No.
Not
Okay.
at all.
CRISPR is a way to edit the genome. Do you know what a genome is?
Yeah, it's the DNA.
DNA is kind of the language that the genome is written in. And the genome itself is an instruction manual. It describes how to make you, how tall you should be, what color hair you have, or what color eyes you have. So what CRISPR is, and an easy way to think about it, it's like a molecular pair of scissors that can go through that long, long genome and find specific places, make small cuts, and edit it. What do you think about being able to edit genomes?
It's actually kind of cool because then you could change, can't you technically change things about a person if you edit the DNA?
Sure. So how do we determine what's the right uses then?
I don't think it should be used for almost cosmetology reasons,
Okay.
or like for people just to be like, oh, I want to be 5 foot.
This is like the
6
conversation we were having in class,
like
huh?
Reasons that aren't
Actually.
necessarily the most important. I just think if it
See, I was at the same level. I was at the teen level. We got it. We nailed it. In summary, honey doesn't suppress collisions, but it can still fit 68 mobs out of the 70 max that'll spawn. So, what does that mean in regards to entity cramming as a setting? So if entity cramming is set to like 25, does that mean that those mobs will despawn?
could genuinely help someone. Like if someone had cancer and there was a way to fix it or like slow down the growth.
So a lot of the work that we do in my lab is about being engineers of DNA. We try and look to see what mutations cause diseases and to see if when we change those mutations, if we can take a sick cell or organism and make it healthy again.
Couldn't you technically, because the P53, when it's defected, that's what causes cancers?
P53 is the most common mutation in cancer. That's right, yeah. That's a great idea, actually, to use CRISPR to target tumor cells and restore P53, to fix that mutation, so to make that cut with these scissors and fix it.
All right, now we're going to get into
Have
some
you
of
heard
the stuff
about
we're getting
CRISPR?
into.
Yes, this revolutionary gene editing tool. I know there have been previous gene editing tools, but CRISPR is more revolutionary in that it's more precise and a little bit more affordable.
Do you know how CRISPR works?
So it works where you have this this Cas9 complex and
Protein, Cas9
yes,
protein?
Cas9 protein complex, along with something called a guide RNA.
That's right, that's right.
And that RNA will basically tell this protein where to go and what gene to sort of cut out.
Right, and this is what makes the CRISPR system very programmable, is
Right.
that the little piece of guide RNA is easy to make.
Right.
We can program CRISPR to go to many different places in the genome quite easily.
From what I've heard, they're like close to almost curing muscular dystrophy with it, but there's a lot of, I guess, ethical issues that come up with it too.
One of the really nice things actually about CRISPR is that we can use it in human cells. You know, if you ask most people, should you use it to cure cancer? Most people would say, yeah, those are good uses. But there are other areas that are a little bit more problematic, like editing the germline, which
Right.
means something that could be passed on.
Ethics-wise, a lot of people will have that natural reaction of fear against something new because it has a lot of potential and we just don't know where it can take us yet. It was sort of similar to like when people started doing in vitro fertilization.
Test tube babies.
Test tube babies.
That was the kind
Everyone's
of scare term, yeah.
Exactly. But now we see it's perfectly fine as long, it's regulated and plenty of people. I know some people who came up from that.
That was college level. That was like a biology major in undergraduate, basically, like maybe second, third year in college, majoring in bio, which is kind of the level that I was explaining it at in class, I feel like. But Ashi and I were trying to research it a little bit more. We want to get to that level 4 or 5. So Creepy, if that's the case, then what I'll do is I'll next time I log on, I'll reset it to 24, because the only reason why it was at 250 was literally because of the zombie spawner that I was using initially, but no one uses it anymore because your farm is substantially more efficient. So.
So there's been a lot of talk about using CRISPR for gene editing in humans, and that can be a controversial thing, I think, very naturally.
There's many aspects of ethics that need to be looked at. Firstly, if we're talking about using CRISPR, are we using it in somatic cells?
I want him to explain the concept, not the ethical piece of it.
Such as T cells, or are we using it in embryos or germ stem cells? And the issue with that is now you're modifying the genome at a germline level.
Any unintended consequences could go forward many generations, you're saying, with germline editing.
Sure, there's unintended consequences, but there's also lack of consent. If you are
not around, you can't consent.
Exactly,
right.
So these future generations or products of CRISPR, they can't consent. Another, I think, ethical component is if CRISPR...
This does not feel like grad level. Because what they're having right now is a conversation about the ethics. I hope they get into the more the technical side of the actual CRISPR Cas9 function.
does make it to market, who will have access to it? Is it going to be cost prohibitive? Will only a certain select few be able to use it?
As many new cancer drugs are today, right?
Right,
Will that be how it is? Yeah.
Would people start using it for non-therapeutic reasons? And I think this then can get into a whole slippery slope.
So I think a lot of people are concerned maybe that CRISPR will be used in kind of frivolous ways, maybe just to choose somebody's eye color or how tall they are, or what color hair they have. And I think what a lot of people don't realize maybe is that the state of genetics is not quite there.
It's nice to think that I can go in and choose exactly what eye color I want, but fundamentally, science doesn't exactly know all of that yet. We don't know every single gene related to eye color, nor the regulatory mechanisms, nor the epigenetics. This is a...
I feel like this woman is coming in and basically just explaining it to him rather than the other way around.
Right, so we can use CRISPR now to try and understand better how do our genes relate to these different features, these different phenotypes that we have. There's a lot of work left to do before we even know.
That's true, Ashi. You can just get contacts.
Dials? What are the controls that affect eye color?
But then you have to put them.
You
but you literally have to put them in every day. People don't like it. Luckily I have perfect vision. I am a genetic anomaly with my vision. I'm just kidding. I have really good vision, so I never have to worry about glasses or contacts. But I know people that have contacts and just they are not a fan of having to put them in. But also, eye color is relatively trivial, kind of as a trait. I would imagine that people, I mean, maybe people care a lot about eye color.
So I think this question right now, even though it's important to discuss, I kind of feel like it's more theoretical right now.
Yeah, or is it really even a point necessary for conversation? Because people are going out every single day and getting plastic surgery to change how they look. How is this any different? And in the same slant, people are using in vitro fertilization, right? So this is manipulating genomes. You're choosing which embryos to implant. So we're almost doing little aspects of what CRISPR has the potential to do.
Okay. That absolutely was not explaining CRISPR at a grad level. They didn't talk about CRISPR. They talked about the implications of it. But what do you? I guess I can't expect much from a YouTube channel. Like, you can't expect. This is a popular YouTube channel from Wired. Like, they're not going to actually get into like the technical. I know, like she came in and she's just like, well, we have to be careful of the ethical implications and the consent factors, and there was no discussion of like, how do you program a guide RNA? There was no discussion of what vector do you use. Should we use AAV or should we use just the regular adenovirus, right? I mean, we've learned, we're well past that. Come on.
So Matt, what are you doing right now in the lab, and how are you using gene editing in your own work?
Right now, one of the questions I've been very much interested in is trying to understand the effect of human genetic variation on using CRISPR-Cas9.
Okay, notice how far we are in the video. We're already at level 5 and we're not even halfway through the video. So what does that mean? Are we actually going to get some juicy deets here? Are we going to really go level 5?
Reagents. Because you and I, just sitting here, differ in millions of different locations within our genome. We use these guide RNAs, which are 20 base pairs, and we match it to different places in the genome. But what if there's a mutation at that site? And how does that affect?
A mutation that's different between you and me. It's the same site, but there's a slight difference in the DNA between you and me.
Different alleles.
Let's say in you, it's a perfect match, and in me, there's one that's actually a mismatch. And how does that affect things in the lab? Because maybe it won't be as efficient, it won't be able to bring Cas9 to the correct site and cut there.
So when people are using CRISPR now in the lab, are they really sequencing the exact cell type they use? Reading out the genome of that cell before they use CRISPR?
Not many do that. It would ultimately be the best way to do it, for sure, because the reference genome that was published in 2001 was kind of just one person's genome. And as we know very well from sequencing.
So in 2001 was a historic time, not just because of 9/11, right? But also because it was the publishing of the first fully sequenced human genome. So basically, they published they figured out the exact order of all the bases in the human genome, right? So there's like, I think 3.6 billion bases in the human genome. And in 2001, the Human Genome Project was finally completed after decade or so of work and a lot of money, but they like published it. They're like, the human genome was published. Actually, you know what? I'll be right back. I have a magazine. I have the Science magazine where it was published in 2001. I'll be right back. Here it is. This is, I don't know if you can read it. This is February 16th, 2001. The Human Genome. This is Science magazine. Inside here, they have, let me see. I think this thing. This insert. This is the human genome. If I unfold this thing, right, that's the human genome right here. This is the entire human genome, I think. I think it's the entire one. Yep, you can. If you were to look at it closely, it has every chromosome. Now, of course, this is a one person's genome, right? An individual's. So it's not exact. It has all the genes that everyone has, but this is going to have like different alleles for whoever this particular person was. I don't even know whose genome it is. How do I fold this thing? I did not fold that properly. But yeah, actually a student gave this to me. So 2001, I was actually your guys' age. I was a freshman in high school, 2001. So, I mean, pretty cool, huh? So in 2001 we sequenced the genome, right? Which was a big deal. 5 hours later, I don't know how big it is. It's big. It's probably like 5 feet tall and 3 feet wide. But it's really tiny. Like the font on here. You can't read it. Yeah, you can't read it. All right. I don't know if he did or not. It's a good question. I don't remember. So let's see what we got here.
Many different individuals, there are a lot of differences. And so there are some concerns that when you use these in the lab that you're intending for a cut to be made in this one place in the genome. But if there happens to be a mismatch there because of some variant in the cells that you're studying, maybe it won't cut there at all. And even maybe worse is that maybe it'll cut somewhere else because maybe now it can match elsewhere.
So you're saying right now that it's kind of early days with CRISPR and that there's a lot of technical issues that really need to be ironed out.
Well, then what you would probably do, right, is you would just sequence that person's genome that you're trying to administer the CRISPR to, and you would make sure that you made the guide RNA with the right complementary basis so that it did match.
That it's not anything can be targeted at any time. We're trying to develop the scientific steps that will take us to that kind of total genome control.
It is still the early days, and as much progress has been done, which is actually quite remarkable given how new this technology is. Yeah. I mean, we're just a few years away from when it was really started being used for these applications. However, having said that, it holds a lot of potential and I think can get there, but there's still a lot of issues and concerns that need to be worked out.
I was going to say that a lot of what inspired me to get into bioengineering are movies like Jurassic Park, which both shows the good and the bad sides of manipulating the nature around us. And so maybe it's a bit of a silly question, but what do you think in our lifetime will we see something like Jurassic Park where humans have actually engineered different animals?
Anything is possible. I'm not sure that we will see that in our lifetimes, but I would be very excited to attend Jurassic Park if that were the case. Having said that, I do think that CRISPR-Cas9 does have a lot of potential to do things that are kind of out of the box. In the past few years, we've been able to tackle ideas that people didn't even think were possible before that. More than anything, CRISPR has created a whole open field of opportunities. And so whether or not that leads us to Jurassic Park, I can't tell you that answer for sure, but I certainly hope that it does.
And I think you're right that the opportunities might be much broader than just biomedical science. It might be things like using DNA as a hard drive, being able to use CRISPR as a diagnostic instead of just a tool for editing. Can we use cells to record data over time with CRISPR? Can we use CRISPR to track cells in a developing embryo? I think this is one of the most exciting recent uses of CRISPR I've seen that I would have never predicted a year ago. The dominant paradigm right now is CRISPR is just for cutting DNA. But when you think of it more as a general platform, a pointer to a location.
Well, it depends on which Jurassic Park you're talking about. The original one or what? I missed it. He said he didn't see it.
In a genome, then that becomes a very, very powerful thing. Do you think CRISPR will be helpful for understanding human variation beyond what we already have just by sequencing people's genomes?
Yes, absolutely. I think that the real power of CRISPR lets us to follow up on this genetic information.
So this whole video has been exceedingly misleading. It said they were going to explain CRISPR at 5 levels. If you're an expert in CRISPR, I want you to tell me the molecular underpinnings of it. Like, they didn't go into any of the detail.
That we've been studying
learned
and
nothing
following
from this
for
video.
a very long time now. There have
We
been a
literally
lot of studies where you
learned
take a
nothing.
group of people with disease X and people without that disease, and you see if any mutations seem to be preferentially in the group with the disease and kind of absent in the group without the disease.
People have observed these differences, but what you're saying is with CRISPR, we can now test, is this causal, this factor? If we make this mutation, does it cause the disease? Does it either create sickle cell anemia or ameliorate sickle cell anemia and prevent it? Do you think we'll ever be at a place where, based on looking at someone's genome and these kinds of CRISPR functional screens, we can predict what kinds of diseases these people might get 10, 20 years in the future?
I think that's certainly a great goal. As of now, we tend to focus on variants or mutations that we know the function.
What about mutations we've never seen before? Something that comes from, let's say, UV radiation and melanoma or something.
I think that we will ultimately have the power to do that. And so thinking about when you start from a mutation, do you look at the expression of RNA? Is that changed? Is it changing things at the protein level?
So this is interesting. So you mentioned that we can analyze genomes, the DNA level, and then you said the RNA level, looking at the expression of genes, and then the proteins, the products that they actually make with proteomics or mass spectrometry. But do you think it's kind of like another level of understanding the function of the genome, or do you view it as part of one of those levels?
I do think it provides a different level of data. The ability to rapidly and genome-wide assess and make changes at the DNA level, and then look at the resulting changes at the RNA and protein level, I think is something that we haven't been able to do, and is now, I think, going to rapidly advance understanding at a genetic level, at the DNA level, of a lot of different diseases.
So you and I have done functional screens. We've done these large-scale CRISPR screens where we modify many genes, thousands of genes, or thousands of locations in the genome, all in kind of a test system. But do you ever see this one day, the idea of these multiplex pooled CRISPR screens going into the clinic, that we actually take a clinical cell line, a cell line from a patient?
Absolutely. I think that is kind of one of the ultimate goals. Ultimately, it would be very nice to be able to correct the mutations for these diseases we've known about for sometimes hundreds of years, and we just haven't been able to do anything about.
There's a lot of kind of ethical issues surrounding, very reasonably, using CRISPR in the clinic.
I think there's a lot of concern about trying to use CRISPR technology or other genome technologies to make humans designed in a specific way, whether you want to change eye color, height, or things like that. The kind of irony of that situation is that the genetics of a lot of the traits that are, you can see.
Here's what I've taken from this video. Levels of difficulty just means how long you talk about it. So this is an expert level because they're talking about it for longer.
See by just looking at a person are quite complex and are not worked out in the same way.
So you're saying that the ethical problem is not really right now a clear and present issue, because for many of these perhaps a little bit more superficial traits that we have, we don't really even know what genes can control these traits. Though it's probably a good idea to start thinking a little bit about engineering somatic cells.
I mean, I'm sure he's a salesman for it because
germline
he's
cells, which are
like an
passed
expert
on
in
to
it.
future generations. And I think one nice thing is that most scientists agree that.
So he wants it to be like more popular.
We need to focus on somatic cells, which
more
really
funding.
impacts a lot of people with these diseases, and that there's many issues around editing the germline, where there you're doing something that might be inherited for many generations.
So it's kind of an interesting misconception that people think that CRISPR is just one thing, just one enzyme, Cas9.
I think that's a really great point, and that speaks to just how fast this technology is developing, because it started with us just knowing about Cas9, but in
just one Cas9, right? S. pyogenes Cas9 was kind of the first one used for gene editing in human cells.
Exactly, and just in the past few years, this toolbox has now been expanded well past that. For example, you can look into other different species of bacteria to find Cas9.
So Cas9 is over many different species.
It's over a tremendous amount of bacteria. And so you had referenced Strep pyogenes Cas9. Well, if you look into Staphylococcus aureus, you can also find Cas9. And that Cas9 is just slightly different. It can target different regions of the genome. And so that opens up a whole new set of possibilities in terms of genome editing.
So it increases the targetable space within the human genome. You can target more regions that you couldn't with that first Cas9. And what I find actually is a really interesting thing is that there's this huge metagenomic diversity of different CRISPR systems. And most of them are really just not even well characterized yet. And I think the best example of that, we were talking about it earlier, is this new RNA targeting CRISPR. So instead of cutting DNA, it targets RNA.
And I think this is just one example of a complete paradigm shift. I don't think anyone had necessarily predicted at the beginning that this would be one of the things that just was created and existed in nature, and it just took some time for people to uncover it.
I think it's a good example of why it's important actually to fund basic science, because you sometimes, when you start down a certain path, you never know where you're going to end up in the end.
The more research that can be done in this area can really unleash new possibilities, finding new things, different versions of Cas9, or other things that function like Cas9, or things completely different that at this moment I can't even think of. The possibilities are endless, to be a little cliche about it.
No, literally, I think they are endless, for sure.
I think it's great for people of all ages to understand CRISPR and at least a little bit about genome.
Okay. All right. Comments? Level 1, what you learn. Level 5, what you get on the test. I feel like a lot of these comments aren't really actually like representative of what happened in the video. I mean, I don't think most people that are coming in and watching this video are really looking for an expert level understanding of CRISPR. And I don't think that the purpose of making this video by Wired is really to have an expert level of understanding of CRISPR-Cas9 system. They need to make a video that's entertaining. So what's entertaining? It's not the technical details of it. It's more the ethics and interesting applications. So, and they would lose people if they started going into the technical thing, because people would get bored by it, because people don't really care. People say they want to be informed about certain things, but they only want to be informed at a level in which there's not much effort required. That's kind of the main issue. Is like to really be informed, you have to put in a lot of effort and energy into understanding something. And for most people, they just either don't have the time or the inclination or the desire to do that. Right. Whereas like a video like this, where we watch this one.
GC content.
Right. Like this is expert level because you're talking about like how to actually make the guide RNA and what is recommended for a good guide RNA. Like, oh, make sure the guanine and cytosine content, the G's and the C's in the guide RNA is between 40 and 80% because that makes it a better hold.
Typical range is between 40 to 80% GC content. A higher GC content stabilizes.
Now, this is too much. This is like way too detailed. Like, I don't. This is something that you don't really need to know unless you're actually going into making these kinds of things. But yeah, I mean, there's definitely a difference between a popular video, a video that's done for popular consumption, like the Wired one, versus a video that's done for actual people that are trying to figure out how this works at a level that is technical and a level that is deep. And it's just not going to be as popular because it's just the amount of information you have to know going into this to understand this is already a lot. Right? Like this person just said GC content and didn't even explain what that meant. Now, I assumed that GC content meant guanine and cytosine, the amount of G's and C's in this. I could be wrong, but that seems reasonable to believe. What else do we care about here? Ribonucleic.
So I'm Lorena de Oñate. I'm a postdoc at Wilson Lab. I'm gonna do an editing experiment in cells, human cells, here at the tissue culture room.
Well, I guess everyone's excited about jobs that they don't do every day. Hi, I'm Rima Mendonça. I'm a staff scientist in the Wilson Lab. This is called a peristaltic pump. This is the first step in purification of Cas9. We purify it one way, and then we further purify it, and then we purify it one final way so that we get a pretty clean protein at the end. It's a very long, involved process.
Here's just a good tip for when you're like watching videos on YouTube or you're trying to like learn something on YouTube. The lower the number of views, the more technical and the more accurate the information is probably going to be, right? So you go from a video from Wired that's got like millions of views that is not really giving you that much detailed information about it to a video with less than 600 views where you're actually seeing like a CRISPR lab. So these are human cell cultures. Yeah, that's true. My goal is to make a video that's so informational that no one watches it. That's like, you've reached like peak information when it's literally not viewed at all. It's just the way it works.
Right now what we're gonna do is lift the cells from a plate and then electroporate them with electric charge. So Cas9 can get into the cell and go into the nucleus and edit the cells. Usually cells go with media, cell culture media. We need to warm it up at 37 degrees.
So they're doing, this is ex vivo, right? So they're doing this using a culture of a cell outside in a lab. So they're, yeah, this is. So this is a centrifuge where you put the tube in and then it spins really fast and all the heavy cells go to the bottom, and then you can remove the liquid. See? There's the cells at the bottom. That little blob. Oh yeah, I use centrifuges a lot in college. Yep. If you go into cellular biology, or even any biology, you use centrifuges quite a bit to spin things down. I remember doing that. That's so funny. So she's dragging the vial along the grate there to sort of vibrate it so that the cells break up a little bit and like that she can get them out.
Great, so I'm gonna pipette now Cas9 RNP here, okay?
She's got good pipetting technique.
Right now we're gonna do the electroshock, so Cas9 can get into this.
Just the way she was holding that. She had the tube in between her fingers, hold like that.
And right now we're gonna do the electroshock, so Cas9 can get into this.
So what she's done so far is she's taken the cell cultures, she's combined it with the Cas9 protein, and now she's putting it into an electro. I guess this is some sort of going to pass an electrical current through it. And when you do that, what happens is the cells open up their cell membrane so that the Cas9 can get into the cell. Electroporation increases membrane permeability and facilitates entry of the RNP, which is Cas9 RNP. Oh. No, stop. Oh, my ears. Give me the chills. I have no idea. Maybe, I think that she does that to sort of try and shake it up a little bit to mix it. So one of the reasons why I just didn't want to why I became a teacher and not because and not going into the lab work is because it's a lot of repetitive pipetting into tubes. And I just didn't really, it was just a lot of repetition that I wasn't really a fan of. I mean, it's definitely cool. It's definitely cool. You just have to be okay with sort of repetitive things, you know? Okay. I think I'm done with CRISPR for today. Crash Course has videos. Yeah, well, I'm sure they do. Crash Course is going to be more at a high school level, probably. But they're usually pretty good. I just think I'm kind of crisped out. I'm crisped out on CRISPR. What is this one? It only has 560 views, so I'm like into looking at it.
So in this video, we're going to talk about how biological
This is a high school student, actually, though.
Components are delivered into cells, focusing on the gene editing tool CRISPR-Cas9. But first, it's worth noting that all living systems use a conserved process that is known as the central dogma to produce the functional units of life. The three main components of the central dogma are DNA, RNA, and protein.
These biomolecules are maintained through processes known as DNA replication, transcription, which converts DNA into RNA, and translation, which converts RNA into protein. In eukaryotic cells, DNA is localized in the nucleus, while RNA and protein is most often found in the cytoplasm.
To deliver anything into cells, we have to remember that eukaryotic cells are surrounded by a cell membrane that is designed to keep most things out.
In this video, we're going to discuss various techniques to overcome the obstacle of getting DNA, RNA, and protein into cells.
So why do we even want to deliver outside molecules into cells?
Well, a scientist may want to introduce DNA, RNA, or protein.
Interesting. Anyway. Yeah, I just bought this one, so I'll probably play this one for a little bit first before I look into another one. Yeah, was that helpful? Okay, I hope it was. It's really, if you get into the technical side of it, it's very complicated, and it's probably you really have to really go through the whole process of understanding it from the beginning to the end, which means that you'd probably, to really have a full grasp, have to go through and take, university classes and all that stuff. But I think you kind of get it at like a level that is good enough for now. Let's start out on easy. Bye, Ashi. Have a good one.
Just give me a target. Sweet.
What does this button do? Oh, powers.
Awesome.
Did I unlock Banana Farm yet? No, I don't think so. I didn't unlock most of the stuff down here yet. I haven't played long enough. I'm going to be curious to see if easy difficulty is too easy.
Awesome. What next? What's up?
Can I place this one here? Is it? Monkey sub. What's the bet? What are the good what are good paths for upgrades? Adds extra pierce and damage. Automatically triggers powerful missile attack. Advanced intel allows long-range targeting of your other towers. Oh. Airburst darts. Sniper, which is the one?
Sweet. Yes?
I think I'm good right now on camo ones because I've got 3 things that can detect camo. Maybe I'll do a ninja. Wizard is good at hitting camo. I don't have wizard. I gotta get that one.
Nice.
What the heck? That was weird.
Incoming!
Wait. What's the difference between the difficulty levels? Just the number of rounds? Because that was only 40 rounds versus 60. Oh, lives and starting money? Lives and starting money? That's it? So I probably could have beat that on. Oh, maybe I'm not. Let's do that one again. I just want to kind of test difficulty levels. See how it is on medium. Is there not a way to, like, part of me doesn't want to have to click like the next round each time. Like, I kind of wish it would just go forward. Wait, disable nudge mode?
Are you kidding me? Nothing. Yes?
Is this... Should I always have this guy? Probably, right? Oh no, it is number of rounds. Medium is 60 rounds. It was only 40.
Yes. Awesome.
That's an okay skill. Oh, but it's not. I see. I didn't realize it's not attacking when it's submerged. So basically,
yes.
That makes sense. Yeah, submarines are really good because they're able to attack. Yeah, you're right, actually. Plutonium reactor. Whoa, submerge to detect camo. Pop balloons and reduce plutonium. So if this basically allows you to get the submerge, the benefits of this without the downsides of it being unable to attack. Am I understanding that correctly? No, I'm not understanding that. Oh, okay.
Incoming!
Ooh, this looks good. Location of all nearby camo permanently. Fortified ceramic balloon. Probably want more.
incoming!
That was easy. These submarines are pretty overpowered. Once you have these upgraded, these submarines, like, they just snipe everything and anywhere on the map. And these things are pretty good against those mobs. Oh, shoot. wait. Oh, I'm good. I'm chill. Thy wizard.
BFB incoming!
What is BFB? Wait, so which one should I unlock first? You said banana farm? Generates bananas each round that convert into game money to spend on more stuff. Oh. There's supports. Okay. That was pretty easy, huh? It seems like a good strategy is to go subs and then turn these cannons into Moab destroyers, and then place some slowing agents at the front, like the glue guys and the freeze guys, and then scatter a little bit of camo, and then maybe place more wizards earlier to reveal camo. Yeah, exactly. That wizard was wasted over here. I should have put him over the front. So let's try that one again, but on hard, and let's see how we do, just to see the difficulty. Standard. Okay.
Are you kidding me? Nothing gets past my bow.
Oh my god. Bruh. This is actually a lot harder.
Yes!
Place this here.
I am Quincy, son of Quincy.
Actually, I should save up for that wizard. How much is that wizard? I don't really need it quite yet.
Yes.
All right, we're going sub, early round sub here. Banana farm is how much? 13.50.
Oh yeah.
Should I save it for a banana farm? Like the earlier you get the banana farm, the better, because then it just generates you more money. All right, does it matter where this is placed? Hold on.
All right.
So if I place this, it doesn't really matter, right? It's support, so I could just literally place it way up here in a place that doesn't matter. Oh, I didn't read the tip. Clicked out of it on accident. Wait, I don't have to click on them. Oh, I just have to get my cursor close to them. Oh shoot, lead. Oh no. Well, I can get lead. Wait. Shoot, I didn't place any cannons down. Nothing I have. I don't have any money. Wizard, but the wizard didn't have fireball.
Come on.
Okay, do this better. All right, so yeah, probably the farm wasn't. I probably should have spent all that on that farm. Yeah, I probably should have got. I forgot about these cannons for lead.
Are you kidding me? Nothing gets past my bow.
I'll move him later. Dang, dude.
Sweet.
That was actually a bad placement.
Yes! Awesome!
Grows 2 extra bananas, punches per round. Bananas last 30 seconds before rotting. Easy collect. The collection radius is larger. Is there a way to auto do this so I don't have to like worry about collecting him? Once you hit bank,
coming! Seriously?
Shoot.
Nice.
Okay, so unfortunately, that was messed up. Wait, what is that? Why does that sound like that? Adds extra piercing damage to commander and all subs in its radius. Oh, I don't have it. I thought I had enough. Why does like a guy keep popping up there? It's like weird. I'm trying to figure out what that. $27,000. Is that worth it though? Probably, right? Awesome. I'm gonna save up for it. 27 grand.
Incoming.
Still a ways away. I didn't see you get that hydrate. Jeez Louise, I actually need to get some. I'll be right back. I need to get some water. Thanks. All right, geez, Louise, take it easy. Yeah, I gotta. After this, I'm gonna go. I think I'm gonna call it a night because I told myself today that I would go for a jog for like a half hour. So it's getting late and it's kind of cold, so I need to do that before 9. So I'll finish this and go for a jog. I'm trying not to use my heat in the house, but I'm freezing. All right, let's see if we can make it through here. I was saving up for the commander of one of these subs. Also, I want to get the bank, the money bank, monkey bank. That interest, sweet interest. Uh-oh. Let's slow it down for a sec here. Let me take a look. That got further than I wanted to. Oh wait, I don't even have to collect bananas anymore? That's actually really good. Just automatically stores it.
PFC incoming! Is that all you got?
Oh, I collect from the bank. I see. I was trying to save up for the $27,000 sub commander. Save up another $4 grand.
Awesome.
I'm hoping I can make it that far.
Headshot.
Seem to be doing okay right now. Oh yeah, you're right. I shouldn't withdraw. I'm stupid. I didn't realize that that's the way it was working. The longer you leave it in, just like Brill money, like it accrues more interest. Yeah, it makes sense. All right, here we go. Tier 5 monkeys are the most powerful in the game. You can only have one of each path in a play at a time. Okay. Okay, now we can invest in other stuff.
Headshot. Oh, headshot.
Moab Assassin. Yeah, I was gonna say that looked really good.
What next?
That looks good. Ooh. Dragon Death is good. Spews endless flame. Yeah, that's, I don't know. This is interesting, right? So the balloons come back and let's try this. Oh, and we can afford Dragon's Death too. Oh, and they go the reverse direction.
Headshot.
Wait, is that being wasted right now? What's the limit on the cash that can be held in here?
Awesome.
Okay.
Headshot. PFC incoming.
Yeah, I guess I'll just let it run and see how far I can get. Oh, right, I think it said right there. Dude, it won't even let me read that. What? Why can't I read that? It only pops out for like 2 seconds. What does it say? 10,000, but you have to pay it back over time. Gives you 10,000, but you have to pay it back over time. Oh, it's a loan. I tapped and hold, it wasn't doing anything. It just goes away. Oh, it's gonna be 40 degrees at 8 p.m. Oh my god, it's gonna be so cold. Oh well. Looks like we're gonna make it. I'm gonna collect. Just in case, put one here. Looks good. It has a loan ability, which isn't interesting. I was just curious about how much it can hold, but doesn't say. Oops. All right. ZOMG. Surely this is the largest thing the Bloons could possibly send at us, right?
COMC incoming. Awesome.
That was not that hard. I mean, there was a moment, right, where I almost lost. But other than that, like once I had everything fully set up. So it seems like there's a pretty good strategy here of going early in the route, putting in things that slow things down. Glue and ice is good. Having a wizard that like reveals camo completely and forever. Throwing in a couple of these big guys and then maxing these subs out and then just having some sprinklers on the end. Seems pretty good. Okay. All right. Good night, guys. I will see you all next week. And enjoy the rest of your weekend. Have a good Sunday. Stay stay warm. I'm going to go try and not freeze my face off for about 30 minutes while I go for a jog out there. But then I'll come back and I think I'm going to take a bath tonight. Something to warm me up after I go for a run. All right. Peace. Be with y'all. Have a good one. I'll see you.